Session 4, question 1. This time we're looking at a different planetary system on the basis that the datasheet says that there are other similar ones. It has 3 confirmed planets and 2 unconfirmed ones. So first off, we've got a table of values to 3 significant figures for the 3 confirmed planets. So if we start off, then we've got r cubed, so that should be 75.2, r cubed, and r cubed. Reason for doing them, all the r cubed ones together rather than doing them in pairs, is so that you remember what you're doing. T squared, these still only need to be 3 significant figures. And 1, 6, 7. So the numbers that we've got here aren't quite as nice as they are for the TRAPPIST-1 system. So plotting our points, I've gone up in 20s along the bottom, in 200s along the bottom and 20s up the side. So I'm expecting, I've got 1 point that will be there, I've got 1 point that will be there, and I've got my other point which is going to be significantly further away over here. We've then got a line of best fit. Now, in exactly the same way as last time, we've got this on our y-axis, that is our gradient, that is our x value, and we don't have a plus c, so we're expecting this to go through the origin. So we should have a nice line of best fit. Goes through the origin and goes through our furthest point. So when we come to be calculating the gradient, we can use 0, 0 and this point up here. So by using your graph or otherwise, so we're going to need to find out what our gradient is. So for part C, we know that k is equal to, and if we use our 2 points as 0, 0 and the furthest point that we've got, because it conveniently went through that, then we're looking at 1, 7, 6, take 0, and the one on the y-axis also take 0. And that gives us a value of 0.132. When we were dealing with the TRAPPIST system, you're looking at expecting it to be around 0.4, but as this is the Gillespie system, we've got a different value of k. However, in exactly the same way as last time, when we've got to express t squared in terms of r, we are allowed the t, we are allowed the r, but we are allowed no other letters. So for part D, we can substitute in and we get t squared equals our value of k, r cubed. So the average distance of the furthest unconfirmed planet from its sun is this many kilometers, so that is going to be equal to r, and we need to find the length of its orbit. So we've got our equation, So we can go with r equals 32.8. So t squared equals value of k, substitute in, and that's cubed. So 0.132 times 32.8 cubed. So that is going to be t squared. So from there, if we want to find t, we are going to have to square root this. 7.96. So we can square root that, and it comes out at 68.2. Okay, so for part F, sorry, that was in days. So for part F, we know the orbit is 32 days, so that is going to equal t, and then we need to find the distance. So they will give you enough pages to be able to do this. It's just that when I printed it out, I didn't leave myself enough space. So for part F, we know that t is 32, so we can substitute this in, and we'll have 32 squared, r value of r, and then r cubed. So 32 squared, no, 32 squared is 1024, and we're going to need to divide that by 0.32, and that will give us r cubed. So r is going to be the cube root of that, the answer divided by 0.132. So that's the cube root of 7757.57 reoccurring. So we're looking at the cube root. So we're expecting a distance of about 19.8 million kilometres.